Okay, we're starting chapter 3, vectors. Um, I just got back from Albuquerque and I drove an RV all the way, and that's pretty. You look on Google Maps and it shows you which roads to take. But had I gone in a plane uh, by RV, it was about 363 miles to get to Albuquerque. If I had gone in a plane, I would have needed not only the 363 miles, it probably would have been less, 350 miles or 320, but I would have needed a direction to know which way to go. It would be uh, I don't know the exact direction. It was basically northwest of San Antonio. So that defines a vector, a magnitude, how far to go and in what direction to go. That defines a vector. So that's what we're going to be talking about right now. They give it a little example in the beginning of the book about sailing a boat. Same thing as I just said with an airplane. But we're going to start by talking about coordinate systems. And we're all familiar with the Cartesian coordinate system. It's a rectangular coordinate system. A point is determined by XY coordinates. If you look at point P, the one at the top, XY, is just a general point. If you look at point P, it's 5 units over and 3 units up. If you look at point Q, it's -3 units to the left and 4 units up. And the units you're to determine what those are. Are they centimeters? Are they meters? They could be inches. You determine what they are. We'll be using different units. Sometimes it'll be force on the y-axis and mass on the x, or it'll vary, and you'll get those instructions as we do the experiments or problems. Okay, so this is a Cartesian coordinate system. It's a rectangular coordinate system, but there's also polar coordinate systems. Um, so you can represent, if you look at figure A on the left, there is an XY up at the top, but you can also define it by an R, a radius from the origin, and an angle that the R is rotated. We usually use the positive x-axis as our reference point, and we measure theta in a counterclockwise direction. So as it goes up, it increases in theta. If it were to go clockwise, it would be going in the negative theta direction. But that is it in polar coordinates. If you look on the right, you see the basic right triangle with R is the same R as on the left. That's the radius from the point of origin. And it has components. It has an X component horizontally and a Y component vertically. And if you look at theta, the sine of theta is Y over R. So it's the opposite over the hypotenuse. Cosine of theta is X over R, and it's adjacent. It's adjacent to theta, adjacent over R. And the tangent theta is Y over X. And we'll be using these throughout. Now, to generate the X and Y, you would use this formula. X is equal to R cosine theta, and Y is equal to R sine theta. So that's how you go from polar to rectangular. Now, if you start with the rectangular, you can figure out the angle. The angle tangent theta is equal to the arctangent of Y over X. And R is equal to the square root of X squared plus Y squared, the old Pythagorean theorem. Okay, so these are good equations to memorize and sort of use. Let's look at a sample problem. The Cartesian coordinates of a point in the XY plane are XY equal -3.5 and -2.5 meters, as shown in the figure. Find the polar coordinates of this point. Okay, so we conceptualize, the drawing helps us conceptualize the problem. We wish to find r and theta. Based on the figure and the data given in the problem statement, we expect r to be a few meters and theta to be between 180, oops, I'm sorry, I accidentally pressed it. I didn't even notice that it was advancing. I was resting my iPad on the keyboard. We expect it to be between 180 and 270 degrees. In other words, we expect it to be in the third quadrant, counting from the upper left corner is first quadrant, second quadrant, third quadrant, and fourth quadrant. Why the third quadrant? Because they're both negative. Both the x value and y value are negative, so that puts it in the third quadrant. Based on the statement of the problem and the conceptualized step, we recognize that we are simply converting the Cartesian coordinates to polar coordinates. We therefore categorize this example as a substitution problem. Substitution problems generally do not have an extensive analysis step other than the substitution of numbers into a given equation. Similarly, the finalized step consists primarily of checking the units and making sure that the answer is reasonable and consistent with our expectations. Therefore, the substitution problems, for substitution problems, we will not label, analyze, or finalize steps. So we use the Pythagorean theorem to find r. The Pythagorean theorem is r equals x squared plus y squared. You'll see that minus 3.5 and minus 2.5, they both, the negatives disappear because we're squaring them. And if you carry out the calculation, you get 4.3 meters. And tangent theta is equal to y over x, so it's minus 2.5 over minus 3.4, and that's equal to 0.714. If you take the arctangent of 0.714, you'll probably get something in the first quadrant, but you'll have to add 180 to that to get 216. And that, let's see, is that, I think that ends this section. The next section will be vector and scalar quantities. So let's stop the share.